So we're going to take a look at the reduction of an amide with lithium aluminum hydride. So the product of this is actually an amine. So net what's going to happen is we're going to add 2 hydrogens to this carbon. So it's very similar to the same reaction that happens with a carboxylic acid, lithium aluminum hydride. Slightly different maybe a slightly different mechanism, but the first thing that's going to happen is your lithium aluminum hydride. That's going to be your nucleophile, and so you're going to have an H minus, and that's going to react with the carbon of the carbonyl group. So addition. Right, so the goal, it's nice to know right away if you know this is going to go to this, because you need to add hydrogens here, right? You know you need to add hydrogens there. So that's part of the thing you're thinking about trying to do. So you add hydrogens there. So we have a tetrahedral intermediate, and we also have AlH3. Do we have any good leaving groups in this tetrahedral intermediate? No, not really. But what we did create was aluminum with 3 bonds. So what happens is actually this O minus will bond to the aluminum. Right, because if you think about it, right, aluminum doesn't have a full octet. So now there's a minus charge in the aluminum. Nitrogen is still here. So at this point, you can do a couple different things. One of the options could be that now this became kind of a better leaving group, right? Aluminum oxygen bound aluminum becomes a better leaving group. We can bring these electrons down and kick this out. Now I'm not actually, you know what? I'll be honest, I'm not that thrilled with this. Let's not do that. Because I don't want to create a plus charge, right? And I don't want to create a bunch of other charges. So I don't like that much. What other options do we have? So instead of going down that really, really super charged pathway, let's take this H is going to take that hydrogen off of the nitrogen. So what's that going to give us? That's going to give us O, aluminum, H. We also made H2 gas there. Where's my negative charge at now? On the nitrogen. Now that feels a little better. Now let's have those electrons come down. Now we'll kick out that species. So now what do we have? From that point we have... Now we have like this imine. And we have this O minus aluminum species. And you could use this, or you could use another lithium aluminum hydride if you want to, but there's a mechanism here that you could say, okay, these electrons come down, and then that fires that H minus towards that carbon of the imine. Or you could do another one of these would react, another lithium aluminum hydride would react with this. But so what would the product of this be? Now you've successfully added the 2 hydrogens to that carbon of the original amide. That weird aluminum oxide kind of species. And at this point, right, there's nothing left to do. That's when the second step of all these, right, step 2, usually is water or H+. That's going to protonate that, and that gets us to that final product, amine. Taking a look at another reaction. So, right, on our Mount Carbonyl, we have acid chlorides, we have anhydrides, we have carboxylic acids and esters, and we have amides. So here we have an anhydride reacting with a secondary amine. So what will this form? So one of the biggest things, you should be able to look at starting materials or look at products and say, oh, this could have came from that, right? Be able to recognize the reactions in such a way that you can not just know the mechanism or have to do the mechanism to figure out the answer. You should be able to look at this and be like, oh, boom, this is going to make what? An amide. Right? You should look at this right away and be like, oh, that's an anhydride, that's an amine, that's going to go down the mountain, that's going to be a downhill process, I'm going to make an amide. All right? You should be able to look at that and know that right away. So that's the product. That's one of the products. It's not the only product. But you should be able to look at this and be like, oh, boom, I know what this is going to make. Because we're reacting an anhydride, which is pretty reactive, good leaving group, right? Nucleophilic acyl substitution. That's going to be our electrophile, the carbon of one of the carbons of the anhydride. So it doesn't matter which one we pick of the carbon of the carbonyls. But the amine is going to be my nucleophile. So this would be considered basic, acidic, or neutral conditions. Neutral, right? It's neutral. There's no charges to start. All right? There's no negative charges like a basic conditions. There's no strong nucleophile like in basic conditions. And there's no H plus like acidic conditions. Right, so when I say acidic and basic, I mean charged. We're definitely going to have charges here, but overall we don't have a charge. So the first step is going to be an addition step. Make sure we balance our charges. We form a tetrahedral intermediate. Tetrahedral intermediate, we ask ourselves, what's my best, is there a leaving group, and what's the best leaving group? What's the best leaving group right now? The thing we just added, right? That's the best leaving group. Well, that doesn't help us. That makes us go back to where we started. So that we gotta do something before we do an elimination. So what do we need to do? We need to do a proton transfer. So we're going to put that proton on the O- because that's the most electron-rich place. So now we have a tetrahedral intermediate. Now we want to look for our best leaving group. So what's our best leaving group now? So we have three choices. We have a carbon, an oxygen, and nitrogen. Straight up periodic table question, electronegativity question. Oxygen, right? Electrons come down, do that elimination. Not only is it an oxygen, it's also an oxygen. It's going to have what kind of stabilization is going to go on here? Resonance. That's right. Elimination. Plus charge on the oxygen. What have we made? We made a carboxylate. Balance our charge. Last step would be just to do a deprotonation. That gets us our final amide product, and then the other product here would be a carboxylic acid. Good. So what if we had an anhydride and we wanted to react anhydride and maybe turn into a carboxylic acid? So we could do that by having an anhydride react with water, and we don't need to use a catalyst here. You could use H plus or like an OH minus, acidic or basic conditions, but you don't have to because you're going essentially downhill. So anhydrides are reactive enough. It might take some time, but you can actually, you could boil this in water, maybe it'll go faster, right? But this will turn into a carboxylic acid, right? Two of them. If you look at the picture, you'll make two of them for every one anhydride. You're gonna make the same carboxylic acid twice. So this would be essentially neutral conditions. So the first step is just gonna be, you do it from this one, addition. make a tetrahedral intermediate. Notice here, what's our best leaving group? Best leaving group is the thing we just added. So we're going to need to do a proton transfer. I'll draw the arrows in this time. You know, this weird looking acetal now, and we have you ask yourselves what's the best leaving group. So now we have 3 oxygens and a carbon, so we know it's not the carbon. But which oxygen should we pick? The one that's could do resonance after it leaves, right? We can do this all in one step. What's that going to give us? That's going to give us our carboxylate, O minus. But we also just created H plus, so guess what? They're going to come together. And the other thing we made was the other carboxylic acid. All right, so then you get your 2 carboxylic acids. All right, there you're done. So you can turn that anhydride into a carboxylic acid with just using water. Probably a little bit of heat would help, but I mean, in theory, right, it's going downhill, so you don't need acidic or basic conditions or even heat to do this. I mean, it'll take some time, but you can get there. That's why if you have a bottle of maleic anhydride, I've had bottles of anhydride before where if you don't close it and it's humid in the lab, you start to hydrolyze it and start turning into carboxylic acid, so you got to be careful with some of these things. Let's review an ester reacting with dibol, diisobutyl aluminum hydride. So in this one, the first step, because this is not aluminum with a negative charge, it's not a charge here at this point. This hydrogen is not that reactive. So usually what happens with dibol, you actually, to activate it when it reacts with esters, first of all, we should know right away where we're going. We're going to the aldehyde and the alcohol. And this is usually step 1, and there's a step 2 with an H plus and water type step. But it's good to know right away what we're going to, right? Dibol is a little more of a mild reagent than something like lithium aluminum hydride, which takes an ester and turns it into an alcohol. This will take an ester and turn it into an aldehyde, so it stops along the way. So instead of adding 2 H's here, we're only going to add 1. Okay, so the first step, because this isn't that reactive, we need to essentially get this reactive. So we draw that resonance form of the ester, and that's going to form a complex. So now that oxygen is bonded to that aluminum, so there's a plus charge on this oxygen and a minus charge on the aluminum now. Now, even though there's a negative charge on the aluminum, it's really electron rich where? It's really electron rich on that hydrogen. So that's where we're going to do that addition step. Make a tetrahedral intermediate. Right, so we made that tetrahedral intermediate. Then we ask ourselves, what's our good leaving group? In this case, we know we're getting to the aldehyde. We want to break that aluminum-oxygen bond. And so the aluminum's going to fall off, and we're going to kick out that oxygen. That's going to give us the aldehyde right away, that elimination step. We're also going to make, which is going to rapidly come together, this O minus and the aluminum. The plus charge. So these two things are going to come together usually. And then if we treat it with H plus and water, we'll end up, the aluminum complex will break down, and we'll end up with the other alcohol that was on the other side of the ester as a final product. So esters to aldehydes with dibol. So essentially what happens is when these two are going to combine, then once you treat with H+, the mechanism is a little more complicated than I want to show you, but essentially what's going to happen, you're going to release the alcohol and get that there. And the aluminum is going to become an aluminum hydroxide, but you don't need to worry about that mechanism. You could have, instead of drawing the alcohol, you could have drawn these two things together too. That'd been fine.